these things. Feeding a 4 ohm resistor. So through a short, 12 volts over 4 ohms. Oh, this, not this again. No. Having technical difficulties here. Great. Oh, this is going to be a really fun class. I'm drawing with my finger. Let's go back here, try this, try hitting a few buttons and see. Oh, yeah, and I got it back. Okay, IL, that's 0 minus. The inductor's still in the circuit. It's storing current, it's storing magnetic field, energy in the form of a magnetic field. So if I want to find the current through the inductor, we could do that. This is a simple circuit to solve, V equals IR. Now we want to look at the T. I've got to remind myself not to actually solve the circuit. It's tempting. At the T equals 0 plus, we've got, now that switch is open. So I've got still the 12 volt source. I've got the 4 ohm resistor. Things have changed suddenly because I've thrown a switch. So my capacitor, I've got to leave that in. It had, oh wait, we'll get to that. And I've got an inductor. And I still have this open circuit over here, which is my air gap. Now, the things we know about the equivalent circuit, we've already learned, is the voltage across the capacitor cannot change instantly. Since the capacitor was shorted out, that capacitor had 0 volts across it. So at T equals 0 plus, it's still going to have 0 volts across it. The inductor had 12 divided by 4 is 3 amps going through it. So the current through an inductor can't change instantaneously. I'm still going to have 3 amps going through it. Okay. If I go to a very long time later, I get the same circuit. Yeah. Can you turn your microphone on? If T is much greater than 0, then basically what I have is I have the 12 volt source. I have the resistor. The capacitor goes back to being open, and the inductor goes back to being a short. And I don't know what the air gap's doing. Now, we want to see what's going on here. The energy in the gap in the coil in this inductor at 0 plus. Well, energy for an inductor, we learned this in 188, is 1/2 Li squared. And at 0 plus, I can look at my circuit diagram, it's 3 amps. And so this is 1/2 times 8 millihenries times 3 squared, a lot of current. And this is basically going to come out to be 36 millijoules. Does not sound like a lot. Let's see what this 36 millijoules can do. I want to find the voltage across the gap if it takes 1 microsecond to spark it. So another thing we know about inductors from 188 is the voltage equals L di dt. So the inductance, we know that, 8 millihenries, 8 times 10 to the minus 3. di, the current's going to dissipate 1 microsecond. So I is going to change by 3 amps. And dt we were given was 1 microsecond, which is 1 mu. That's my shorthand for 1 times 10 to the minus 6th. And we go ahead and calculate that. and we get 24 kilovolts. So when the energy through this starts to run through this loop, because the capacitor is going to block the DC current, it's going to dissipate this energy in 1 microsecond and produce a voltage across that air gap of 24 kilovolts, which is enough to spark the gap, break down air. It's got so many volts per meters is what the breakdown voltage of air is. Okay, so that is one application. We'll go through these problems and solve them in gory detail later, but I just want you to kind of get a feel for where we're heading here. Now here is, wow, how did that happen? I am amazed by technology. Okay, I like that better though. My thing is on the other side now. Another application, this is a series RLC circuit. You can use it as a filter. And a filter, and we'll do that in lab 2, is like a smoothing circuit. If I have a digital to analog converter, and this is what this is going to do. If you've taken 286, you've used these before, it produces these steppy voltages. I change the number on the input and I get a sudden drastic change on the output. If I want to smooth that and get a nice curve going to my circuit, and there's a lot of reasons why you want to do that if it's an analog circuit, what I'm going to do is I'm going to effectively filter it, get rid of the higher frequency components here, and I can smooth it out. So I can use these RLC circuits for filters. I can use them to suddenly switch a lot of power, generate current spikes, or generate voltage spikes. One of the labs, I forget which one it is, we build a later circuit. And basically you have a very small DC source and you're going to use that to generate a huge current spike to jumpstart somebody's heart. It's a simulation, it's safe. Sometimes I used to tell Sharber that just to scare him. Software's built a defibrillator this week. I miss Sharber. Okay. Now these three, you may have seen this in differential equations, you may have seen this in a physics class somewhere, but basically whether it's a series RLC circuit, this is the series version, or it's a parallel RLC circuit and everything's in parallel, I can get 3 different types of damping. And they all have their uses. And I love to write this up on the board and have it all come together at the end, but this is going to be hard to do this semester. Basically, I've got in A, it's bouncing. And I perpetually confuse the words underdamped and overdamped, so you'll hear me like stop to think which one this is, but that's definitely underdamped. So A is underdamped. And it doesn't look, and you can see, if you've ever built a circuit, you've seen things that look like this, little ringing and things like that in there. Underdamped circuit, what it does, if I think about what the final value is for all these 3 circuits, it's somewhere around 35 volts. And A is the one that gets to the final value the fastest. It doesn't stay there, but it gets there. Okay. B, if you look at B, this is called critically damping, is the name we've given this. And the advantage of B is that it settles to within like 1% or 0.01%, whatever you're shooting for. It's going to settle the fastest. Something you'd use for a precision measurement. And C is slower. But C has the benefit, and it's called overdamping. It has the benefit of the best stability. So if I have something like I'm doing the temperature control for a building or something like that, or I don't want it to just oscillate up and down, I want it to hit a stable thing, I would want an overdamp system. Any type of control system, you're usually looking at overdamping. So each one of these has different applications. If I want to change the particular level of damping in a circuit, the easiest way to do it is twiddling R. If I just vary the R value and leave the L and C the same, I can move between overdamping, underdamping, and critically damping. And I did that a lot in the lab. When I was trying to build something, it was a precision measurement circuit, and try to get it as close to critical damping as I could. What I would do is I would actually, in analog circuits, once you build the board, there's all kinds of parasitics that are not taken into account. So you can't really calculate the value of R. You approximate it, build it, and then just change the R value until you get the best damping or the best speed out of it. Okay, so we've got a series RLC circuit. We know the voltage across the resistor, Ohm's law in terms of the current is just going to be IR. Okay, somebody's making a phone call. Yeah, thank you. V equals IR. The voltage across an inductor, and we learned this in 188. It's one of the few equations I had memorized when I was working. V equals L di dt. So L di dt. Now the voltage across a capacitor, and this is going to be a little trickier, because we know I equals C dV dt. I would have to multiply both sides of the equation by C, and multiply by dt. I would get I dt, and then divide by, and we want V, I dt 1 over C equals dV. If we integrate both sides of the equation, we get the voltage across the capacitor is going to be 1 over C times the integral of I dt. Okay, now I want to write KVL around the loop. KVL, sum of the voltages around the loop equals 0. I always go clockwise, it's just my convention. And if I hit a plus sign, I'm going from plus to minus, it's a drop, so I put a minus sign in the top, on the top. So basically, we would have minus VR, and then I'm going across the inductor again, it's minus, so minus VL minus VC equals 0. I could multiply that equation by -1 to get rid of the minus signs. That's a valid equation too. So I write it all down. Oh, this is going to be fun. IR plus L di dt. My handwriting is better than this in real life. Plus 1 over C, the integral of I, and those are all capital I's. Let's just make them all caps. I dt equals 0. Oh, wow. I don't know what I just did. I want to go back to this. Wait, stop it. My computer's going crazy. Draw with touch. Try that one. Draw that one. Oh, great. hate technology sometimes. When you're relying on, I got my 0. All that equals 0. Well, now I've got an integral differential equation, is what the mathematicians call it. In order to clean this up a bit, I'm going to take a derivative of the entire equation. And if I take the derivative of this, I get r di dt, I switch to lowercase, plus L d2I dt squared plus 1 over c times I equals 0. I get a second order differential equation. This is why DiffEq is a co-rec or something like that for this class, or Calc 3 or something. Whatever math gets you here, I forget. So there is my equation. What I'm going to do with that is I'm going to assume a solution, just like you do in differential equations. My solution is of the form some constant a times e to the st. So the derivative of I with respect to t would be, I'm just going to write I prime. I prime would be a s e to the st. And the second derivative, I double prime, is going to be a s squared e to the st. So this math should be familiar to everybody who's made it this far into this class. I plug in the values that I get here, and what I'm going to get when I simplify everything, I plug in for the derivative of I plug in as e to the st. For the second derivative, I plug in as squared e to the st. And for the non-derivative, I just plug in a to the st. I'm going to get an equation that looks like this. And I can factor out a e to the st and the inductance from that equation and end up with this thing here in parentheses. Now, L can't be 0. If the inductor is 0, it's not an RLC circuit. E to the something can never equal 0. That's just a rule of math. Which means in order to make this work, the quadratic equation I have in parentheses is what must equal 0. And we call that the characteristic equation, just like you did in math. And this is the characteristic equation here. S squared plus R over LS plus 1 over LC equals 0. Now we want to find a solution to this. We can find values of S, and then we can figure out what the S is in the e to the st equation. Well, this is a quadratic, and just like we learned in algebra, the quadratic formula looks like this. If I want to find S1 and S2, it's going to equal negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, yeah, and I wrote it. I was teaching 325, the advanced engineering math class. I gave an exam and somebody asked me what the quadratic equation was, and I felt sorry enough for him at that point. I wrote it on the board, and then he looks at me and goes, what's A, B, and C? So I will tell you, A is the coefficient of the S squared term. B is the coefficient of the S term, so A is 1. B would be R over L, and C would be 1 over LC. So we plug those in, and we get S1 and S2. Okay, so S1, S2, two possibilities here. Negative b is negative r over L, plus or minus the square root of b squared, r over L squared, minus 4, a is 1, a is 1, c is L, 1 over LC, all over 2a. Okay. Two solutions. Does it matter which one I pick for S1 and S2? In this case, the answer is yes. Because it will mess you up. Believe me, when I first started teaching this class, this is what really bothered me. S1 is associated, you've got the plus and minus there. For S1, use the plus sign. And for S2, you use the minus sign. And because when we start doing the kind of the plug and chug version, it's going to matter which one we pick. Now we learned this in Algebra 1, Algebra 2 somewhere. There are 3 different types of solutions for this equation based on the relative value of R, L, and C. If R over L squared is greater than 4 over LC, you're going to get 2 real roots. And if R over L squared equals 4 over LC, you get 1 real root. And if, let's just change this here. If R over L is less than 4 over LC, on the same ditto, what we're going to get is we're going to get 2 complex roots. And they'll be complex conjugates of each other. Okay. Turns out, kind of the punchline here, if I have 1 real root, this is critical damping. If I have 2 complex conjugate roots, this is this is under damping. And if I have 2 real roots, this is over damping. Yeah, there's a V in over damping. But that's over damping. So you can look at that immediately, compare R over L and 4 over LC, and determine which type of damping you have. I could vary R by itself and change the type of damping. Okay.
And can that equation be used for both the parallel and series damping circuits? Like,
that is an amazing question. This was derived using KVL on a series circuit.
So that would mainly be for the series dampening circuits.
This is for the series circuit. We won't go through this. I'm not going to do this again for the parallel. I'm just going to give you the result. And there, if you look in BB Learn, there are 4 PowerPoint slides, and I've got them posted to BB Learn under O2 key slides. And this is the piece of paper when I was first teaching this class, and I don't have it with me, that I would walk around with, and this is what I would need to be able to solve the problems. It has all the information you need to solve these problems once you figure out the procedure. And we'll get to that one before the end of class. Okay. Good. So yes, it matters. S1 is the positive version of the quadratic equation. S2, you put the minus sign there. So I've got numbers, and we want to find the roots. So I'm just going to plug in R, L, and C. So what have I got here? For S1, I'm plugging it into this formula. R is 10, 2L is 8, plus the square root of 10 over 8. 2L is still 8. I need to square that and subtract out 1 over LC. 4 henries times a quarter of a farad is 1. And for S2, same equation, I would just change this to a minus sign. So I go through, I plug the numbers in, and I calculate it. And that comes out, S1 comes out to be negative 0.5. Oh, I know what's going on here. I'm getting too close to the Zoom screen. Okay, we'll just write it down here. S1 equals negative 0.5. It has units. Oh my gosh. We won't talk about the units yet. The units are kind of silly. S2 minus 2. We'll call it radians per second. They're negative, which is actually a good thing. Negative S1s and S2s are stable circuits. Positive are unstable. They're associated with, these are associated with decaying exponentials, positive number associated with growing exponentials. Now I'm looking at this circuit, and what I really want is fast assembly time. We want to find a value of R for critical damping. So I've got to solve this equation for R. I get R over 2L. I'm going to move the 1 over LC to the other side. And I'm going to take the square root to get rid of the squared over here. And then I'm going to multiply both sides. Boy, that is really bugging me at this moment. Oh, that's right. Never mind. I have an automatic check, and this wasn't satisfying it, but yeah, this is a little bit different. So I multiply by 2L, and I get R 2L over what over LC? Oh, not this again. Oh, I'm frozen. Okay, we will come back